Hello and welcome to a new video in a course on Galois theory. In the previous videos, we've given an introduction to field theory and we discussed some basic properties of fields. So in this lecture and in the coming one, I'll be going over some survey of important concepts from ring theory, and this includes polynomial rings and related concepts, specifically irreducible polynomials. So here's the setup. We start with a field f, and I remind you, a field f is just a set with two operations where over addition f forms an abelian group, and over multiplication, when we omit 0 from f, we get also an abelian group. So it's actually a commutative ring where every non-zero element has an inverse. What we do is that we consider the set f adjoint x. F adjoint x, it's gonna be the set of all polynomials, so p of x, polynomial in x, such that the coefficients of p are in f. So this is the definition of this f adjoint x as a set. So we take all the polynomials and we require their coefficients to be in f, in the field f. For example, Rx is just the polynomials, the set of polynomials with real coefficients. Alright, so what we're gonna do is that we're gonna equip this set with two operations. The first operation is addition, and the second is multiplication. Now, with these two operations, this set forms a ring, right? It forms a ring. And it's quite easy to see why it forms a ring. So addition and multiplication are defined in the usual way you'd add and multiply polynomials, right? So it's clear that it actually forms a ring, and we proved something similar in a previous video. So it actually forms a ring when equipped with these two operations. However, it turns out that it forms something more interesting than a ring. It's not only a ring, but it's also an integral domain, and we're gonna also claim that it's actually a Euclidean domain. We're gonna prove this, and we're gonna prove and define these in a few. So let us start by noting that this thingy is actually an integral domain. So let me just remind you of the definition of an integral domain. So an integral domain is a non-zero ring that is commutative. It's commutative ring, and it has no zero divisors and has no zero divisors. And recall just what is a zero divisor. A zero divisor, a number a in a ring R, is an element of R, is an element of the ring R that is not zero, and for which there exists an element b that is not zero, such that a dot b is equal to 0. So a zero divisor, again, I remind you, like a and b are called zero divisors if they're both not zero and they multiply out to 0. So this is the definition of a zero divisor. And an integral domain is just a commutative ring, and when we say commutative, we're referring to the multiplicative operation. It's just a commutative ring that has no zero divisors. As an example for you, I remind you that the integers is actually, the ring of integers is actually an integral domain, because you can't multiply two integers. So if m and n are not 0, then if you multiply these, you don't get 0, right? Like if they're not 0, you can't multiply them and get 0, right? This is clear, I guess. So our claim here is that this ring, so if F is a field, then F adjoint X, when equipped with the addition and multiplication of polynomials, it's actually is an integral domain, right? So here's the proof. Of this. At first, we need to show that, well, clearly f of x is not 0. F adjoint x is not 0. This is clear, right? This is not the 0 rank. Also, if you, it's actually commutative. It's clearly a commutative ring. And why is that? Because if you have two polynomials, p of x and q of x, and you multiply these out, let's say this polynomial is the sum of ai x to the I, and this polynomial is the sum of bi x to the I, okay? If you multiply these out, you will get a polynomial with coefficients being some combination of the AIs and BIs, right? So the polynomial you get is one with coefficients being as such, and since F is a field, right? Since F is a field, F is a commutative ring, so we know a field is actually a commutative ring, and so between quote and quote, we can swap the BIs and AIs. So we can do we can swap them as we wish to get that this is the same as q of x times p of x. So this is actually q of x times p of x. It's actually the multiplication operation is clearly commutative. But notice it's very important that we use the fact that F is a field, right? So we have to have that F is a commutative ring. All right, so I'll also leave it to you as an exercise to verify that this thing is a ring, right? It's an easy thing to show. You just need to show that f of x over addition is an abelian group, and f of x take away 0 over multiplication forms a monoid. So I'll leave it to you as an exercise to show this is something that we've shown something similar to in a previous video. So the last thing we need to check to complete the proof here is that we need to prove that there are no zero divisors in this thingy, right? So why is it the case that so we want to show that f of x has no zero divisors. But why is that the case? Well, suppose it does have zero divisors. Let's call them p of x and q of x, both not 0, and p of x times q of x is equal to 0. So let's suppose that. Let's suppose that it does have a zero divisor, and let's derive a contradiction. So let's write p of x as a sub n x to the n plus a n minus 1 x to the n minus 1 plus dot 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 plus a naught, and let's write q of x as b to the m b sub m x to the m plus a plus b m minus 1 x to the m minus 1 plus dot 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 plus b naught. Now since so here's the thing. So here we have the degree of P is equal to n, and the degree of Q is equal to m. So this is what we're assuming, and we can assume that since it's not a zero polynomial. Well, look at this. Since P of x and the Q of x are not zero, and it's a polynomial of degree, P is a polynomial of degree n and Q is a polynomial of degree m, then we know that a sub n is not zero and b sub m is not zero. So this we know for sure, because the way you get the degree of a polynomial is by looking at the highest non-vanishing coefficient, right? The index of the highest non-vanishing coefficient. Anyways, so this is what we have. We have that an and bn are not zero, and bm, excuse me, are not zero, right? And now comes the importance of the assumption that f is a field. Now, since f is a field, we know for sure that f is an integral domain. So this is what we proved in a previous video, integral domain. And since f is an integral domain, it has no zero divisors, i.e. f has no zero divisors, right? So since it has no zero divisors, what can you say about the product of an and bm? What can you say about this product? Well, since they're not zero, then their product is not zero, right? Because otherwise there'll be zero divisors, but in f there isn't any zero divisor, because remember here the polynomials p of x and q of x, these are polynomial in fx, which means these coefficients, the coefficients of these are actually in the field f. So an and bm are in f and they're not zero, so they can't multiply to zero. So an bm is not zero because f has no zero divisors. And since this is not zero, we note now that p of x times q of x, like if you do the expansion of this polynomial by this polynomial, if you do the expansion of these, then the first term is going to be an bm x to the m plus n, and the rest is going to be plus lower degree polynomial. So this is going to be a lower degree polynomial. However, regardless of what this is, since it's a lower degree polynomial, this can never be zero, because this is not zero, and thus this polynomial can never be zero, right? This is not the zero polynomial because, there isn't anything here to cancel this, and this is not zero, so the whole thing is not zero. And what we just proved is that we didn't derive a contradiction. We kind of proved the counter positive of what we need to prove. What we did is that we started with a polynomial p and a polynomial q, and we assumed that or we actually did derive a contradiction. We assumed that these are not zero and that their product is zero, right? But we reached the fact that their product is not zero, so a contradiction, and thus it contradicts the fact that it does have zero divisors. Thus f adjoint x has no zero divisors as desired, right? So this is all we needed to prove to get that this thingy is an integral domain. So this completes this proof. All right. So the next thing we need to talk about is the concept of division algorithm. So you remember for the integers you have that this integer ring, it's a ring. You have what's so-called Euclidean algorithm, right? Or division algorithm. And what it says is that it says for every a, b, and we're supposing that b is not 0, for every a, b integers, there exists unique q and r, where we call q the quotient and r remainder, with r between 0 and less than b, such that you can divide a by b, but with a remainder. So this is what we have. This is called the division algorithm in Z. Now you ask the question, can we divide polynomials like with remainder? Can we do the same for polynomials? Well, it turns out that you can, as long as your coefficients are coming from a field. If the coefficients are coming from a field f, then you have the division algorithm in f adjoin x. You have the division algorithm in this thingy. So let us see why. I mean, I don't wanna do the whole of rank theory here in one lecture, but it's kind of good to give you the idea of what's going on. Just because it's a very important proof, I'll just give you the idea of the proof here. Let me just state what I'm gonna prove before I prove it, I guess. So we're starting with two polynomials, f of x and g of x, and these are polynomials in this ring, right? It's the polynomials of the ring of polynomials or with coefficients in f, and f is a field. So we're supposing f is a field. This is important. So we're gonna also assume, analogous to what we assumed here, we're gonna assume that g is not 0. Then there is a unique, just follow what's going on here. There's a unique quotient. There's a unique quotient and a remainder polynomials, such that I can divide f by g with a remainder r, where the remainder can either be 0 or it must have a degree strictly less than the degree of g. So remember, so just observe here, the distinction here is that the Euclidean function, so to speak, is different, right? So here we're talking about numbers, and we're requiring that the remainder has a smaller magnitude than the thing we're dividing by. Here, to make a similar notion, like we can't say a polynomial is less than another polynomial. What we're gonna say is that we're gonna say that the degree of the remainder is less than the degree of the thing we're dividing by. All right, so let me just give you the idea of the proof, because it's a very important proof actually. Real quick, we have the function f of x. Let's write this, well, this is a polynomial, so let's write this as an x to the n plus an minus 1 x to the n minus 1 plus dot 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 plus a naught, okay? And we have the other polynomial g of x, which is, let's write it as bm x to the m plus bm minus 1 x to the m minus 1 plus dot 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 plus b naught. So both of these are polynomials in the ring fx, which means these coefficients, the ai's and the bi's, are actually in the field f. So let me just mention this. The ai's and the bi's are in f. And we wanna prove that we can do this. We wanna prove that there is a q and an r that where we can do this division, right? So what we're gonna do is the following. We're gonna try to induct on, so first of all, let us assume that the degree of f is bigger than or equal to the degree of g, because if the degree of g is bigger than the degree of f, we can just take q to be 0 and r to be f, and that's it. Now let us assume now the degree of f is bigger than or equal to the degree of g. And what we're gonna do is that we're gonna try to form an induction argument, right? We're gonna try to say, well, let's suppose that it holds for an f with degree less than n, and let us prove it for n, okay? So suppose it holds the statement, I mean, it holds for polynomials less than with degree less than n, and we're gonna try to form an induction argument. So let us do that. So here's a very nice trick. So since we're assuming that since g of x is not 0, right, and we're assuming that it's of degree m, we have that bm is not 0, right? But remember, bm is in f, which means that bm inverse exists, because f is a field, and thus every non-zero element has an inverse. Now let's take h of x to be a n bm inverse x to the n minus m, and I'm gonna make it clear why we're taking this polynomial, okay? So this polynomial is also in fx, okay? I hope that this is clear. So let us look at f of x minus h of x times g of x. If you notice here, if we multiply this by this polynomial here, the first term, like this times this, is gonna be the an is gonna stay, bm's are gonna cancel out, and x to the n minus 1 with x to the m is gonna be x to the n. So maybe I should leave some space here, and we're subtracting this. So we have a minus here, right? And we're gonna just have f here plus lower degree poly, and here we have plus lower degree, let me just say minus lower degree poly. Like, it's coming from the expansion, and this is coming from the rest of the term. Like, this thing is the rest of the term of f, and this thing is the rest of the terms of hx times g of x, okay? So the first term and the second term, these terms will cancel out, and we'll be left with a lower degree polynomial. Lower than what degree? Lower than n. It's lower than degree n, and thus we can apply the induction hypotheses. We can apply the induction hypotheses to this thingy and finish the proof, okay? So I'll leave it to you as an exercise to fill in the blanks in this proof, okay? So long story short, if f is a field, then fx in the ring fx, we have the division algorithm. And this is very important to recall and to keep in mind, because it's gonna be very useful as we go in the lectures. All right, so the next thing I wanna remind you of is what's so-called Euclidean domain, okay? So there is nothing very special about the ring fx. It's just an example of a Euclidean domain, right? So what is a Euclidean domain? So here's a definition for you. A Euclidean domain is just an integral domain let me just say, for which, between quotation, the division algorithm holds. So if you have an integral domain where the division algorithm holds, then we call that a Euclidean domain. And we've just shown that the ring fx is actually an integral domain, and the division algorithm also holds for it. and thus fx is actually a Euclidean domain, right? And this is very important. And the reason it's very important, the reason we're introducing Euclidean domain or the concept of Euclidean domain is that we're very often interested in what's so-called a GCD of two polynomials. So just as we have for numbers, just as we have GCD of two numbers, like GCD of 2 and 6 is 2, so it's the greatest common divisor of the two. So let me just remind you in general, what is a GCD? Well, a GCD is a number that divides both numbers that you have, and it's the greatest such number, right? So you ask yourself a question: Can we have a GCD of two polynomials? So the answer is yes, but let me just give a formal definition, and then I'm gonna tell you why, right? So here's a definition. Let F be a field. Let F be a field, and let's say and let P of x and the Q of x be polynomials in the ring fx. And let's assume that these are non-zero. Okay, so these are non-zero element. Then d of x, which is equal to, it's defined or denoted as the GCD of P of x times Q of x, or the greatest common divisor of these two polynomials, is the unique monic polynomial. I'm going to define by what I mean by this. So by monic I mean, i.e., the coefficient of the leading term is 1. So the coefficient of the x with the highest power is 1 in the polynomial. So d of x is going to be x to some power, then plus constant times x to that power minus 1, and so on. So it's the unique monic polynomial that satisfies two properties. First of all, d of x divides P of x, and d of x divides Q of x. Okay, so it's a common divisor. However, there's a g here. It's the greatest. So it's the greatest in the sense that if d prime of x divides P of x, and d prime of x divides Q of x, then d of x, d prime of x gotta divide d of x. Okay, so in this sense that d is the greatest common divisor between these two. And just to clarify here, when I say a polynomial f of x divides g of x, I mean so let me just write it here, because just I want to remind you of it. When we say g or f of x divides g of x in f of x, if we're talking about the polynomials over this field, we say that f of x divides g of x if there exists a q of x, a polynomial q of x, but it's very important that this polynomial is in f of x, right? Such that g of x is equal to f of x times q of x. Okay, so very often the way you're gonna show that a polynomial divides another is by applying the division algorithm that we know it holds for f of x, right? We know it holds here. So very often we're gonna apply the division algorithm and get a remainder and try to form some argument to show that this remainder must be 0 and thus f of x must divide g of x. But the definition is given as such. It's that there exists another polynomial where f of x times q of x is g of x. So this is the definition of the GCD. Now, why does it exist? Why is it possible to find the GCD of two such polynomials in such a ring, right? So I remind you, the reason or the way the way one might prove the existence of a GCD for integers, for example. So here, if we're talking about integers, the way we're or the one way of arguing for the existence is using existence use the what's so-called extended division algorithm. So what you do is that, just as a reminder from the integers, what you do is that you start by setting r naught equals to a. So say we wanna find the GCD of a and b. Okay, so say we wanna find this. So what we're gonna do is that we're gonna start by setting r naught to be a and r1 to be b. And then we're gonna repetitively apply the following. We're gonna take ri plus 1 to be ri minus 1 minus qi ri. So what we're doing here is, what we're doing in this step, in the ith step, is we're dividing ri minus 1 by ri with remainder ri plus 1. So every time you will have ri minus 1 and ri, just as here you have r0 and r1, and you'll be getting qi and ri plus 1. Okay, how are you getting these? By the division algorithm. Okay, I hope that this is clear. So you have you have ri minus 1 and ri, okay, and you'll be getting these q's and r's by applying the division algorithm repetitively. Okay, and speaking of which, ri plus 1 in this case is going to be less than ri, and it's non-negative. Okay, so as you see, the ri plus 1 or the ri's are decreasing, but they cannot decrease forever, and thus there should be an integer, positive integer k, such that rk plus 1 is equal to 0. So after repetitively applying this division algorithm, we get rk plus 1 equal to 0. And and you might have seen in an abstract algebra course or in a number theory course that rk is the GCD. So the last non-zero remainder you get is the GCD of A and B. Okay. And the same thing applies when you want to find the GCD of polynomials in the field fx, in the ring, fx. So this is all I wanted to mention about Euclidean domain. So just to recap here, we started with ring fx, and we proved that it's an integral domain, and then we proved that the division algorithm holds in fx. And then what we did is that we said that this fx is just an example of what's so-called a Euclidean domain. And in general, in Euclidean domains, we have the notion of GCD. and GCD is just the greatest common divisor, and it's defined as such. And one way of getting the GCD is by what's so-called the extended division algorithm. Okay, so this is a recap of what we did so far. And these are very important concepts. This is why I'm going over these kind of very carefully.